Moment by parts method, as the method indicates that it is moment by parts, not the entire moment diagram at a time. The method is applied when the loading situation is asymmetric. I would like to refer that as a complex loading situation. In this case, we really don't know how the deflection curve will look like. It's gonna probably look something like this, not really a symmetric one, so it's going to deflect a little bit more this side than the other side. So in that case, when you draw a tangent line, we cannot really tell. It's very difficult to use that moment area moment method. So what it is done in this case is to use moment by parts. As you can see here, the moment is calculated only for load RA. So if we take moment with respect to point B, and that with for that 15 kilo 1000 pounds more load, it's going to be 300 pounds, and we follow the same convention when you calculate the moment. For example, we are only calculating that 15k load, and then that is from B, it is the distance is 20 foot. We use the same cutting convention. If it's a cut here, so there is another moment applied here to balance that. So M at B, sorry, that's B. So if we do this anti-clockwise, you see that 15k will do a clockwise moment, and this one is anti-clockwise. So summation of all this moment, if we do that, MB is equal to 0. So we can write 15k times 20. That's a negative moment because that's clockwise, and then MB is anti-clockwise, which is positive. So these are all equal to 0. So we can say MB is equal to plus 300. It is very important to have plus minus, because when you use the formula, then minus, we have to subtract that. So for that 15 kilo pound load, 1000 pound load, the total moment is 300, and because it's a concentrated load, the moment is called y equal mx plus c type of equation. The load equation is a constant, so y equals constant b. Sorry about that. Or we can say simply load equals p equals constant, or b, and then we moment is 1 degree more, because moment is load times distance. So it's a first degree equation like this, a triangle. Same thing for 10 kips, it's gonna do a negative moment if we follow the same cutting principle. For that distributed load 3 kips per feet is gonna do a negative moment too, if we do the same cutting principle. And then we draw like this by parts. So we draw a moment diagram for this 15 kips, draw a moment diagram for this 10 kips, which is here, this one, and then draw a moment diagram for this uniformly distributed load, which is here. So we draw a moment by parts, and then we calculate whatever we need to calculate. Now we could also work from the right side. So this one was work from the left side, like our normal convention. That's the thing we use. We could work from the right, and either way it's gonna be the same. Or we could work from both sides, left and then from the right, and then middle, meet somewhere in the middle, like in this case. So it is however, in that case, what you have to do is use one of the point of interest to approach. So you can come from the left side, come from the right side, and just meet at one of the point of interest. So you could make this point as a point of interest and meet there, or you could make this one and meet there. Either way it's gonna work. So it's kind of flexible method because it's by parts, so you're not adding anything. Next video I'll show you how to use that to calculate deflections.